Welcome back to the Deep Dive. Today we are plunging into, well, the highly structured but, let's be honest, often chaotic world of bringing a product to life.
That's a good way to put it.
Whether you're thinking about a highly complex piece of machinery, maybe a new consumer gadget, or even a sophisticated service, that journey, from just a raw idea to a profitable commercial product, it's anything but random.
Absolutely not. If you want to succeed, you really need a
Bully
playbook.
playbook. Okay.
And what our source material immediately establishes is that successful product development isn't just about, a single moment of genius or some burst of invention. It's really a disciplined, multi-stage process.
Systematic.
It's a systematic activity, exactly, that has to integrate multiple disciplines, often all at the same time.
And the foundational concept we're tracking today, the one the sources really hammer home, is total design, which they define as the entire necessary systematic activity required to transform a market opportunity, that initial spark, into a finished, manufacturable, and commercialized product. So we're essentially giving you a complete step-by-step playbook that successful organizations use globally.
And that systematic playbook, that total design concept, it really demands a profoundly interdisciplinary approach. You just can't do it in silos.
Okay.
It requires the seamless coordination of three central functions. First, you absolutely need marketing. They're the ones identifying opportunities, defining market segments, and crucially, deeply understanding customer needs.
Got it. Marketing first.
Second, you need design and engineering. These are the folks specifying the exact geometry, the materials, the tight tolerances required, all the technical nuts and bolts.
The how it works.
Precisely. And third, you absolutely need manufacturing. They handle process planning, the supply chain, critical cost estimation, all that how we actually build it affordably aspects.
And if any one of those legs wobbles,
the whole thing can fall apart. If any of those three functions break down, the total design fails. Simple as that.
Okay, let's unpack this process then, because it is structured. The generic model outlined in our sources, it breaks down the entire product development timeline into a logical sequence. 6 phases, right?
That's right. 6 core phases. It's a pathway that transforms, often ambiguous inputs into really precise outputs at every single stage.
So what's phase 1?
It begins with planning. This is where you link the project to any advanced research and, critically, produce the project's mission statement. That's the key output.
Okay, planning sets the mission.
Then you flow into concept development. This is where the search for solutions really happens. Ideas are generated, brainstormed, explored, and the best ones are selected.
The creative but structured part.
Exactly. Third is system-level design. This is where you define the product architecture. How do the pieces fit together?
Modular versus integrated, that kind of thing?
Precisely that. Fourth, we get into detail design. Now you're specifying every single material, every manufacturing process, every tolerance, down to the last screw.
The nitty-gritty.
Fifth is testing and refinement. This is where prototypes are built and evaluated against those specifications you said earlier. Does it actually work? Does it meet the targets?
Make or break time.
Often, yes. And finally, 6th phase, production ramp-up and launch. This is the moment the product hits the market at full scale, getting the factory running, filling the channels.
Okay, that's the roadmap. 6 phases. But before we jump into phase 1, planning, we need to touch on something you mentioned earlier, how organizations actually structure themselves to tackle this. It's complex, it's cross-functional. How does the total design team actually get organized?
That's a crucial point. Teams typically fall into one of 3 common structures. First, you have functional organizations.
Okay.
Here, people are grouped purely by their expertise. So all the electrical engineers report to the head of electrical engineering, mechanical engineers to the head of mechanical, and so on. Very traditional silos.
Got it. What's the second type?
Then you have project organizations. This is almost the opposite.
Yeah.
Everyone is grouped entirely around the specific product they're building, regardless of their specialization. They all report to one project manager.
Total focus on the project.
Right. But the sources note that for the most complex projects, the ones demanding deep technical specialization and rapid cross-functional communication, the most common structure is actually the hybrid. It's the matrix organization.
Ah, the matrix. Sounds complicated.
It is, and it has its challenges. The matrix structure is fascinating because it tries to get the best of both worlds, but yeah, with inherent complexity.
How does it work?
Individuals in a matrix organization actually report to 2 managers.
2 bosses.
Essentially, yes. They have a functional manager, maybe the head of software, who controls their technical development, training, career path. And they have a project manager, say, the leader for the new gadget project, who controls their day-to-day tasks and output specifically for that product.
So it balances expertise with project focus.
That's the goal. It allows the team to maintain deep technical expertise within functions while ensuring the intense focus needed to meet a project deadline. But like you said, it introduces challenges. Dual reporting, potential conflicts over resource allocation, who gets priority. It requires really good management.
Makes sense. And that structure, functional project or matrix, it dictates how the work actually gets done, how the team operates.
Absolutely. And regardless of the formal structure, successful execution depends on the team itself. You generally have two layers. There's the small, focused core team.
The decision makers.
Usually, yes. The key leaders from different functions. Often small enough, maybe 6 to 10 people, that they can meet in a single conference room and make decisions quickly.
And the second layer.
That's the much larger extended team. This includes external suppliers, key internal staff who contribute specialized knowledge, maybe consultants, manufacturing partners. For something really complex, like developing a new aircraft, that extended team can easily number in the thousands.
Wow. Okay, so that sets the stage for how the people are organized. Let's dive into the process itself. Part 1. From opportunity to measurable goals.
Right. Phase 1, planning. You absolutely cannot start the next phase, concept development, until you have a clear, high-quality opportunity identified and formalized. It sounds obvious, but it's critical.
And the sources describe this crucial front-end process using a powerful metaphor, which I liked, the tournament structure of opportunity identification.
Yes, the tournament structure, it really captures the reality, doesn't it? Most initial ideas, frankly, are not great, but you need sheer volume to find the brilliant ones hidden in there.
So you start wide.
You start very wide. You generate a large number of raw opportunities, sometimes 50, sometimes hundreds, depending on the scope. You simply can't afford to invest heavily in all of them.
Right.
So you rigorously filter them down through stages. You explore the feasibility, the market size, the strategic fit of the most promising ones. It's essentially a multi-stage funnel designed to efficiently kill bad ideas early.
Brutal, but necessary.
Exactly. While giving the potentially great ones enough oxygen, enough resources to survive that initial vetting process.
The Frolicat example they mentioned really illustrates this perfectly, a pet products company.
Right. They were tasked with creating new pet products. So they started with, I think it was 50 raw opportunities, just brainstorming ideas.
50 ideas. And after running them through this tournament structure, filtering, researching, how many actually launched?
Just one. A successful, commercialized, swinging ball toy for cats.
Wow, 50 down to 1. That's a 2% success rate.
It really shows the necessary brutality, as you said, of that filtering process. You have to be willing to let go of most ideas to focus on the winner.
And critically, generating high-quality opportunities isn't just an internal brainstorming session, is it? It requires looking outwards.
Absolutely. It requires proactively studying the market and, maybe most importantly, the user. The sources really highlight the value of techniques like user anthropology or consumer ethnography.
Which basically means watching people.
In a structured way, yes. It means actually observing and documenting customers in their natural environment, using products, facing problems. This method is far, far superior to simply asking them what they want in a survey or focus group.
Why is observation so much more powerful than just asking? What's the difference?
Because customers usually articulate needs based on their current reality, their existing frame of reference. They tend to ask for incremental improvements. Make this lighter, make this faster, add this feature.
Okay.
Anthropological study, however, reveals the constraints they're operating under, the workarounds they're currently using, maybe even things they struggle with but don't consciously recognize as a problem. And that points directly to potentially revolutionary, unarticulated needs.
The kind that lead to breakthrough products.
Precisely. The bicycle industry provides that classic illustration. Shimano, the big component manufacturer.
Right, I remember reading about this. They didn't just survey current hardcore cyclists, did they?
No, because they knew what they'd hear. Make the bikes lighter, give us more gears. Performance optimization for the existing market. Instead, they used user anthropology to understand why people don't ride bikes in the first place.
Okay. Focusing on the non-consumers.
Exactly. That completely reframes the design challenge. If you're designing for existing riders, you optimize performance metrics. But if you're designing for non-riders, you have to address fundamental barriers.
Like what?
Things like fear of maintenance, fear of complexity, all those gears and cables, maybe even just physical discomfort or safety concerns. The resulting product is fundamentally different. It's less about racing geometry and shaved grams, and more about simple utility, reliability, ease of use, maybe even integrated lights and locks.
That shift from just optimizing an existing category to actively addressing barriers to entry, that seems like where the really high-quality opportunities lie.
That's the hallmark of finding them, yes.
Okay, so you've gone through the tournament, you've done this deep user research. What's the tangible output of this entire planning phase?
The formal output is the project's mission statement.
The mission statement.
This document is the single necessary input required to formally kick off Phase 2 concept development. It essentially charters the team. It defines a target market clearly, identifies the key business goals, things like target profit margin or expected sales volume, and it sets the high-level performance metrics and constraints.
So locks in the general direction.
It locks in the direction, yes. It ensures that all the subsequent expensive engineering work is focused on the right target and aligned with the business strategy. Hashtag 1.2, uncovering customer needs, the voice of the customer.
Right. The mission is set. The team has its charter. Now, they need to capture the voice of the customer. This is where we start taking those, sometimes ambiguous desires, I want a better bike, and begin turning them into something more concrete.
Yes, and this isn't just casual conversation. The sources detail a rigorous 5-step process for converting those raw customer inputs into actionable needs. Structure here is key.
Why is structure so important at this stage?
It's critical for avoiding scope creep later on, and perhaps more importantly, for preventing misinterpretation of what customers really mean. Everyone on the team needs a shared, validated understanding.
Okay, so what are the 5 steps?
Step 1 is gathering raw data from customers. This requires carefully selecting the right customers representative of your target market and eliciting information, usually through interviews or observation.
Step 2.
Interpret that raw data. The raw data might be direct quotes, observations of behavior, maybe even photos or videos. You have to interpret these into structured, succinct customer needs statements. Always phrase them in terms of what the product needs to do, not how.
Got it. What, not how. Step 3.
Organize those needs into a hierarchy. You might have hundreds of need statements. You need to group them logically, perhaps into primary needs, secondary needs, tertiary needs. Create some structure.
Makes sense. Grouping helps manage complexity. Step 4.
Establish the relative importance of those needs. Not all needs are created equal. Some are critical must-haves, others are nice-to-haves. You typically use surveys or other quantitative methods to get customers to rate or rank the importance.
So you know where to focus design effort.
Precisely. And finally, step 5 is reflection. The team needs to pause and review the entire process. Did we capture everything? Did we miss a key customer segment? Did our interpretation introduce bias? It's a sanity check.
That step 2, interpreting the raw data into need statements, feels like where a lot of the analytical heavy lifting happens, especially around those hidden needs.
It is, and this is particularly true when it comes to identifying latent needs. This is absolutely critical.
Why latent needs specifically?
Because if a team only focuses on meeting needs that are explicitly articulated by customers, the things they directly ask for, they'll likely produce an incremental product, something that maybe just catches up to the competition, but doesn't leapfrog them.
But if they can uncover and satisfy those latent needs,
then they have the potential to produce something truly revolutionary, something that delights customers in unexpected ways.
Okay, remind us again, what exactly are latent needs?
Latent needs are those the customer may not express or maybe can't even articulate. Why? Well, maybe because they just assume the current standard is fixed and can't be changed, so they don't bother asking. Or maybe they simply don't know that a better solution is even technologically possible yet.
So they're unarticulated because the customer doesn't know they need to articulate them.
Exactly. They haven't imagined the possibility.
Can you give us a really tangible example? Something high value.
Sure. Think about smart home devices. Let's take thermostats. The articulated needs are pretty obvious. I want to adjust the temperature easily. I want to save energy. I want to program a schedule.
Right, the standard stuff.
But the latent needs really emerged from observing users struggle with the complexity of programming those early devices. People didn't explicitly say, I want a thermostat that learns my habits, because they didn't know that was feasible. But through observation, designers realized customers implicitly wanted the thermostat to work pretty well right out of the box with no complex setup. They wanted it to automatically respond to occupancy without them having to manually fiddle with schedules all the time. These were the latent needs.
And when products like the Nest thermostat address those,
It completely changed the game. Meeting those latent needs defined a best-in-class product and significantly raised the bar for the entire category. But finding these requires that deep ethnographic work, that observation. You won't get them from a simple Q&A session.
Speaking of how you gather this data, the sources seem to strongly recommend interviews as the primary method, especially for the initial deep dive over things like large-scale surveys or even focus groups.
Yes, they do. Interviews are typically less costly per hour invested compared to focus groups, but maybe more importantly, they allow the development team members themselves to establish a crucial rapport with the customer.
Build empathy.
Build empathy, yes, and ideally, experience the product's use environment alongside the customer. Actually see where and how they use it. This immersion is invaluable for spotting those subtle usage patterns and uncovering latent needs firsthand.
That makes sense. But there's an interesting efficiency comparison mentioned too, something about focus groups versus interviews.
Right. The research cited suggests that, on average, one well-run 2-hour focus group typically reveals roughly the same number of distinct customer needs as conducting 2 separate 1-hour interviews.
So focus groups can be efficient for just generating a list quickly.
They can be, yes. They can be a useful tool for rapid generation, or sometimes for allowing managers or stakeholders to observe customer reactions directly and simultaneously. But you trade off something.
What's the trade-off?
You sacrifice the depth, the context, the rapport, and that detailed use environment experience you get from doing one-on-one interviews in the customer's own space. And crucially, the sources strongly caution against relying solely on written surveys for these initial efforts.
Why not surveys? They seem efficient.
Surveys are great for validating hypotheses you already have, or for getting quantitative data on preferences among known options. But they are inherently limited. They rarely, if ever, reveal the unanticipated, the truly novel, the revolutionary latent needs that define market leadership. You have to go deeper first, #tag 1.3 translating needs into precise specifications.
Okay, so we've done the qualitative work. We've gathered these, sometimes fuzzy goals expressed in the language of the customer. Now comes the technical translation challenge. We have to move from those desires to specifications.
Yes, precise, measurable details that the engineering team can actually design to.
This feels like a really critical conversion point in the whole process.
It is arguably the most critical conversion point in the entire total design process. You're moving from the product needs to feel light to the product mass must be under 1.0 kilograms. Specifications are literally the bridge between that deep market understanding and the technical execution.
And the first step in building that bridge is establishing target specifications. What are those exactly?
Target specifications are essentially the preliminary goals. They're the ideal targets that the team sets before a final product concept has even been selected.
So they're aspirational at this stage.
They are aspirational, yes. The team knows that the exact final values might need to change based on the specific concept that eventually gets chosen. Technical trade-offs are inevitable. But these targets serve as aggressive benchmarks. They're used to compare competing concepts during the selection phase that comes next.
How do you set these targets? Is there a process?
Yes, there's a structured process, typically 4 steps.
Right.
And it begins, crucially, with preparing a meticulous list of metrics.
Okay, the metrics list. Let's detail that. What makes a metric useful here? What defines a good metric?
A good metric must reflect, as directly as possible, the degree to which the product actually satisfies a specific customer need. It has to be specific, it must be quantifiable, and ideally, it uses objective, unambiguous units. Well, for a need like, the product should be quiet. The metric is sound level, measured in decibels, dB. For the suspension should absorb bumps well. A metric might be damping coefficient, measured in newtons seconds per meter, NSM. For the operation should be fast, the metric is time, measured in seconds. If you can't objectively measure it, it really can't be a specification.
But I remember the suspension fork example from the source material. It had metrics like instills pride. That sounds incredibly subjective. How do you handle something like that in a technical specification document?
That's a great question, and it highlights where you need to be creative but still rigorous. For these subjective factors, like pride or maybe visual appeal or ease of use, the team typically uses proxies and market weighting. Yes. For instills pride, you can't measure pride directly with calipers. But you can run customer surveys using carefully designed scales, asking the target demographic to rate how much pride they feel owning or using the product concept. So the specification might become something like, visual equity score must achieve 4.5 out of 5.0 based on survey results from target demographic A.
Ah, I see. So the metric itself, the survey score, is numerical and measurable, even if the underlying need is subjective.
Exactly. You can run the survey and get a number. It then forces the design team, particularly the industrial design team, to use their aesthetic judgment and design skills specifically to achieve that target score. It treats aesthetics not just as decoration, but as a measurable performance attribute, weighted according to customer importance.
Okay, so you have these target specs. Then presumably after a specific concept is selected, these targets have to be finalized. They become the final specification.
Correct. And this step is where engineering reality really kicks in hard. It's not trivial.
Why not? What's involved?
Because the final specifications absolutely must be technically and economically realizable with the chosen concept. This requires two critical inputs that likely weren't fully available when setting the initial targets.
Which are?
First, you need detailed technical performance models. And second, you need reasonably accurate cost models.
Okay, let's start with the technical models. What are we talking about there?
These are the rigorous engineering analyses needed to predict if the chosen concept can actually hit the target numbers. For mechanical components like that suspension fork, this might involve complex fluid dynamics analysis for the damper or thermal modeling or detailed stress analysis for durability.
And this is where computer simulation comes in heavily.
Absolutely. The sources emphasize the critical role of high-powered computer simulation tools like finite element analysis, FEA, or finite element modeling, FMM.
Can you briefly explain what those are?
Sure. FEA, or FEM, essentially takes a complex physical object like a metal bracket or a plastic housing and digitally breaks it down into thousands, sometimes millions, of tiny, simple geometric shapes, the finite elements. The computer then uses complex mathematical equations to calculate how each tiny element responds to applied forces, heat, vibration, whatever you're testing. By summing up the behavior of all these elements, it can predict, with remarkable accuracy, how the entire part will physically deform, where stresses will concentrate, how it might vibrate, or even when and where it might fail under load.
And this is all done before building a physical prototype.
Exactly. That's the power. It allows the team to iterate digitally, to optimize the design, to explore trade-offs, and to converge quickly on technically optimal specifications that ensure safety and performance targets are met, long before they cut any metal or mold any plastic. It saves huge amounts of time and money.
Makes sense. And the second requirement for final specs was cost models.
Yes. Critically important. Engineers can design the most technically brilliant product in the world, but if it costs too much to manufacture, it fails the total design mission. It won't be profitable.
So you need early cost estimates.
You need reasonably accurate cost models, yes, like the preliminary unit cost estimates they established for each component of the suspension fork. These models are required to ensure that the final specification allows for adequate profit margins at the target market price.
So finalizing specifications isn't just setting a number, it's an iterative optimization process.
It absolutely is. You're constantly iterating, converging on values that optimize the product's competitive position, maximize the value delivered to the customer based on those needs you identified, and, crucially, guarantee the required profitability for the business. It's a balancing act informed by engineering models and cost models.
Okay, so we've navigated the crucial front end. We have our mission locked down. We understand our customer needs deeply. And we've translated those into precise, measurable target specifications. Now, finally, we get to generate the solutions, the concept generation phase.
Right. And the goal here is not just to stumble upon one good idea. The real goal is to ensure the team explores the full space of possible alternatives as early and as thoroughly as possible.
Why is exploring the full space so critical at this stage?
It's fundamentally about risk mitigation. It's defensive, in a way. Imagine if a team settles on a concept quickly, invests heavily in developing it, and then, late in the process, they stumble upon a vastly superior approach they missed earlier.
Ouch. All that time and money wasted.
Exactly. It's devastating. Or maybe even worse, what if a competitor introduces a dramatically better product because they did a more thorough search and found that superior concept that you missed? You lose market share, competitive advantage, potentially everything.
So thorough, systematic exploration early on prevents those costly surprises later.
It significantly mitigates that risk, yes.
Okay, so how do you do this systematically? The sources outline 5 distinct, structured steps for concept generation. What's step 1?
Step 1 is fundamental. Clarify the problem. And usually this means decomposing the complex overall challenge into simpler, more manageable sub-problems.
Break it down.
Break it down. Think of the example they use. A pneumatic nailer. Designing the whole thing at once is overwhelming.
Sure.
So you decompose it. What are the key functions it needs to perform? Well, it needs an energy source. It needs a mechanism to store the nails. It needs a way to feed the next nail. It needs a firing mechanism. It needs to be lightweight. You break the big problem into these smaller, functional subproblems.
And each subproblem is easier to tackle individually.
Much easier. And the solutions you generate for these subproblems then become the building blocks, the fragments that you'll later combine to create overall product concepts.
Okay, decompose the problem first. Step 2.
Step 2 is search externally. The team absolutely needs to look far beyond their own internal knowledge, beyond their own walls, for existing solutions or solution fragments that might apply. Don't reinvent the wheel if you don't have to.
Where should they be looking externally?
The source material lists several key places. First, talk to lead users.
Lead users.
These are customers, often individuals or niche firms, who are experiencing needs months or even years before the general market segment. They're often pushing the boundaries and sometimes even trying to invent their own solutions out of necessity. They can be a goldmine of insights.
Okay, lead users. Who else?
Second, talk to experts. These could be consultants, academics working in the field, or crucially, vendors and suppliers. You can find them through trade associations, industry conferences, or using resources like supplier databases. Thomasnet and McMaster-Carr are classic examples mentioned. These folks often have deep domain knowledge.
Makes sense. And I imagine technical literature and patents are also high-value sources.
Incredibly valuable, yes. Patents are particularly useful because, by law, they must describe the invention in enough detail for someone with ordinary skill in the art to replicate it. So studying patents gives you deep technical insight into existing, often protected, solutions, what works, what doesn't, who owns what.
So you know what's already out there.
Exactly. You also need to search published literature, scientific journals, conference proceedings, and of course, benchmark-related products, both from competitors and sometimes even from completely unrelated fields that might face analogous problems. Maybe a solution from aerospace could be adapted for a medical device, for example.
Okay, so external search is broad. Then step 3 is the internal search.
Right. Now you tap into the collective knowledge and creativity within the development team and the broader organization. This often involves both individual brainstorming and structured group methods.
Like traditional brainstorming sessions.
Yes, but with some guidelines emphasized in the sources. For group brainstorming, they recommend limiting the group size, maybe to no more than 10 people.
Why small groups?
To preserve effective group dynamics and ensure everyone actually gets a chance to contribute actively. In huge groups, quieter members might get drowned out. And the absolute cardinal rule during brainstorming is suspend judgment.
Don't shoot down ideas too early.
Don't shoot down any idea initially.
Okay.
Most of our professional lives train us to evaluate and criticize quickly, but concept generation requires divergent thinking, requires creativity. Any initial criticism of an idea should be immediately forbidden or, better yet, channeled into a suggestion for improvement. That might be heavy, but what if we use this lighter material? Turn perceived weaknesses into evolutionary steps for the concept right away.
Okay, suspend judgment. That's key.
Yeah.
Now, steps 4 and 5 are about bringing structure to all this creativity, systematic exploration and reflection.
Exactly. You've generated lots of fragments and ideas both externally and internally. Now you need tools to make sure you've combined them thoughtfully and haven't missed promising combinations. This is where you ensure the creativity hasn't just been random.
What are the main tools here?
The two main tools highlighted are the classification tree and the concept combination table, which is sometimes called a morphological chart.
Okay, classification tree first. What does that do?
The classification tree is primarily an organizational tool. It helps you categorize the alternative solutions you found for a single subproblem. Remember breaking down the nailer.
Right. Energy source, nail storage.
Okay, so for the energy source subproblem, your classification tree might branch out. Chemical, like combustion, electrical, battery-powered, corded, pneumatic, compressed air, manual, spring-powered. It just organizes the options for that one piece of the puzzle.
Got it. And the concept combination table? That sounds like where the synthesis happens.
It is. This is often where the real magic of generating novel concepts occurs. This table, or chart, takes the solution fragments you've generated for different subproblems and helps you systematically combine them to synthesize new, overall product concepts.
How does it work visually?
You typically list the key subproblems down the left side. Energy source, nail storage, firing mechanism. Then, across the rows next to each subproblem, you list all the different solution fragments or types you've identified. OG for energy source, battery, air hose, gas cartridge.
Okay.
Now, by tracing paths across the table connecting one solution from the energy source row with one from the nail storage row and one from the firing mechanism row and so on, you can systematically generate a huge number of potential overall concepts. Some combinations will be nonsense, but others might represent truly novel approaches the team wouldn't have thought of organically.
So it forces you to consider combinations you might otherwise miss.
Exactly. And the sources note it's particularly effective when you focus on combining solutions for coupled subproblems, those subproblems whose solutions strongly interact with or constrain each other.
Makes sense. And the final step, step 5.
Step 5 is reflection. Before moving on to actually evaluating and selecting concepts, the team needs to pause again. Look back at the process. Do we feel confident that we've really explored the solution space thoroughly? Did we consider enough external sources? Did we use the combination tools effectively? It's a final check to ensure they've done their due diligence before committing significant time and resources to the next phase, which is selection. Hashtag 2.2, critical evaluation and concept selection.
Okay, the team has done its homework. They've systematically generated, let's say, 50 or maybe even 100 potential concepts. Now the goal shifts completely. You can't develop all of them. You need a rigorous, repeatable way to select the winner, or maybe the top few contenders.
Absolutely. This is concept selection. It's the formal evaluation process where you screen and score those generated concepts against the customer needs and the target specifications you defined earlier. The output is one, or perhaps a small handful, of concepts chosen for further, more detailed development.
And the process usually starts with a rough initial cut, right? Using something called the Pew concept selection process.
That's right. The Pew process, or concept screening, is excellent for that first rapid filtering when you have a large number of fairly rough concepts.
How does it work?
It uses a simple screening matrix. You list your potential concepts across the top. Down the side, you list your key selection criteria derived from customer needs and target specs. Then, crucially, you choose one concept as a common reference concept.
A baseline for comparison.
Exactly. This baseline might be an existing competitive product or maybe just a simple, obvious concept the team developed early on. Then, for each criterion, you evaluate every other concept relative to that reference using a really coarse scale. Is it better, plus, worse, or about the same?
Plus or minus 0. Very simple. What's the power of this simple screening?
Two things mainly. First, it's fast. You can screen a lot of concepts quickly without getting bogged down in detailed scoring yet. Second, that forced relative comparison really highlights the core strengths and weaknesses of each concept in relation to a known benchmark. It makes the differences pop out.
And it's not just about scoring, is it? Something about generating new ideas during the process.
Yes, that's a key strength. The Pew process explicitly encourages creativity during the evaluation. As the team discusses why concept A is better than the reference on ease of use, but concept B is better on durability, they often realize, hey, what if we combine the user interface from A with the robust mechanism from B?
So new hybrid concepts can emerge right there in the meeting.
Exactly. You generate a new concept on the fly by combining the best features of others, add it as a new column in the matrix, and then reevaluate. It's iterative and aims to constantly improve the pool of concepts being considered.
Okay, so Pew screening gets you down from, say, 50 concepts to maybe 5 or 10 really promising ones.
Yeah.
What's next? How do you pick the final winner?
Now you move to a more quantitative stage, typically using a weighted decision matrix, which is often just called concept scoring.
Weighted matrix. Sounds more detailed.
It requires a much finer level of detail and judgment, yes. Instead of just rough plus-minus-0 comparisons, you first need to assign specific numerical weighting factors to each of your design criteria.
Where do those weights come from?
They should come directly from the custom need importance ratings you established earlier. Remember step 4 of identifying needs. The most important needs get the highest weights. Then, for each concept still in the running, you score the degree to which it meets each criterion, usually using a more resolved scale, maybe a 1 to 5 scale, or even an 11-point scale, 0 to 10, for finer granularity.
So you're scoring each concept against each criterion numerically now.
Right. You're estimating how well does concept X satisfy the need for low weight on a scale of 0 to 10. You do this for all concepts and all criteria.
And this matrix effectively translates all these different criteria, which might be in kilograms, dollars, user ratings, into a consistent set of weighted values.
Precisely. That's the core idea. For each concept, you multiply its score on a criterion by the weight of that criterion. Then you sum up these weighted scores across all criteria for that concept.
And the concept with the highest total score wins.
In theory, yes. The concept with the highest total weighted score is considered the best according to this structured evaluation. It forces the team to quantify their judgments, even subjective ones, and it makes the selection process transparent and defensible, linking it directly back to the prioritized customer needs defined in the mission statement.
That seems pretty robust. But the sources mention that sometimes decisions are even more complex. Maybe the concepts are radically different, or the trade-offs are really fundamental, like choosing between lowest possible production cost versus extreme, maybe life-saving reliability. Does the weighted matrix handle that well?
It can struggle when the concepts are very dissimilar or the trade-offs feel almost philosophical. For these really complex, high-stakes decisions, the sources point to a much more advanced, mathematically rigorous tool, the analytic hierarchy process, or AHP.
AHP. Okay, what makes that different or more powerful?
AHP is a decision-making framework designed specifically for complex multi-criteria problems, especially when you're comparing options like concepts that haven't been fully built or tested yet, so there's significant uncertainty. It works by structuring the entire evaluation problem into stratified levels, a hierarchy.
A hierarchy.
Yes, you have the overall goal at the very top, reliable, select the best concept. Below that, you have the main criteria, cost, performance, reliability. Below each criterion, you might have sub-criteria. And at the bottom level, you have the actual concepts you're comparing.
Okay, it structures the problem.
Right.
But how does it improve the actual evaluation or consistency compared to just assigning scores in a matrix?
The key difference lies in how judgments are elicited. AHP relies heavily on paired comparisons.
Paired comparisons.
Yes. Instead of looking at concept A and trying to score its ease of maintenance as, say, a 7 out of 10 in isolation, AHP forces the team to compare concept A directly against concept B on that single criterion. Regarding ease of maintenance only, is concept A strongly preferred over B, moderately preferred, equally preferred, moderately worse, etc.? You use a standardized scale for these pairwise judgments.
So you're always comparing two things at a time on one specific factor.
Exactly. You do this systematically for every pair of concepts on every criterion, and you even do paired comparisons between the criteria themselves to determine their relative weights more consistently.
What did that achieve?
By forcing these direct one-on-one comparisons, AHP mathematically enforces consistency in judgment. It helps mitigate the psychological biases that can creep in when people try to assign absolute scores. It also provides measures of inconsistency, flagging where the team's judgments might be contradictory. It's particularly powerful for structuring decisions where the trade-offs are non-commensurate, meaning you can't easily measure them with a common unit, like comparing a safety improvement against a cost increase.
Wow, okay. That sounds significantly more involved, but potentially much more rigorous for really tough choices.
It is more involved, yes. It often requires specialized software. But for critical, high-risk decisions, that rigor can be invaluable. The overall point of both Pew screening and these scoring methods, whether simple matrices or complex AHP, is to ensure that the final concept selection isn't based on gut feel or politics or who argues loudest.
But on a structured, traceable evaluation linked directly back to customer value and the project's mission. All right, we've navigated the selection process. We have our winning concept, or maybe two top contenders. Now we move into what the sources call system-level design. This is where we define the product architecture.
Yes, and this is a crucial high-leverage phase. The decisions made here about the product's architecture will heavily influence how the product can be manufactured, how easily it can be updated or varied, and even how it's marketed for years to come. It sets the stage for detailed design.
So what exactly is product architecture?
Fundamentally, product architecture is the scheme, the plan by which the product's essential functional elements, what the product must do to work, are arranged into physical building blocks or chunks. And just as importantly, it defines how those physical chunks interact with each other.
Okay, functions map to physical chunks and their interfaces. And the key characteristic you're deciding here is the degree of modularity, right? It exists on a spectrum.
Exactly, it's a spectrum. On one end, you have highly modular architecture.
Modular, like building blocks.
Very much like building blocks. In a modular architecture, the functional elements are deliberately allocated to separate, distinct physical chunks. And critically, the interfaces between those chunks are clearly defined and often standardized.
Can you give an example?
The traditional bicycle is a great example they use. Think about the handlebars. The function of controlling the brakes and the function of controlling the gears are typically handled by separate physical chunks, the brake levers and the shift levers. They're mounted independently, connected by standard cables.
Okay. And what are the big advantages of doing it that way, being modular?
The main advantages are flexibility, standardization, and the ability to easily offer product variety. Modularity allows for straightforward product change and upgrades. A customer or the manufacturer can easily swap out just one component, say, upgrading to higher-end shift levers without impacting the brake system at all.
Makes sense.
It also allows the manufacturer to offer a huge range of product variety relatively cheaply by simply mixing and matching different standardized components. Think of all the bike models built around the same basic frame architecture. That's a key marketing and manufacturing advantage.
Okay, that's modular. What's on the other end of the spectrum?
On the other end, you have highly integral architecture.
Integral, meaning
Well,
tightly combined.
Yes. In an integral architecture, functional elements are deliberately combined and allocated to the same physical chunk. Often, multiple functions are tightly coupled within a single component, and the interfaces between chunks might be non-standard or highly optimized.
Why would you choose to do that? What motivates integral design?
It's often motivated by the pursuit of maximum performance or specific physical goals like improved aerodynamics, reduced weight, smaller size, or unique ergonomics. Performance optimization is usually the driver.
Example.
Stick with the bicycle. Look at the high-end integrated shift and brake levers you see on modern road bikes, sometimes called drifters.
Ah, right.
Yeah,
One unit does both shifting and braking.
exactly. Shifting and braking functions are integrated into a single physical chunk. This allows for a sleeker aerodynamic profile, potentially lower weight, and a specific ergonomic feel. But it's a much more complex, tightly coupled component.
So it seems like there's a fundamental trade-off here. If integral architecture is often driven by maximizing performance, does that mean modularity inherently involves sacrificing some performance for the sake of flexibility and variety?
That is often the classic dilemma, yes. You frequently trade some degree of optimal performance for the benefits of modularity or vice versa.
So how do great design teams navigate that specific trade-off? How do they decide where on the spectrum a product should sit?
It comes back to the fundamentals. Designers must constantly ask, what is the primary value driver for the target customer segment as defined in our mission statement?
Aligning with the mission.
Always. If your target customer is an elite athlete, like a professional cyclist, those marginal gains in aerodynamic performance or weight reduction offered by an integral architecture might be absolutely critical. They might be worth the higher cost, the reduced flexibility for swapping components, and maybe even the increased maintenance complexity.
Okay.
But if your target customer is an everyday commuter or a recreational rider, then the flexibility to easily replace a broken shifter, the lower initial and replacement costs, and the wide variety of compatible components offered by a more modular system are likely far more important than shaving off a few grams or optimizing aerodynamics.
So the architectural decision isn't just technical, it's deeply strategic, tied to the market and the customer.
Absolutely. The architecture chosen must always align with the overall project mission and the specific needs and priorities of the target customer you identified back in phase 1.
And these architectural choices, modular versus integral, they have really profound downstream implications, don't they?
Huge implications. They impact manufacturing strategy. Integrated designs often require more sophisticated, specialized manufacturing processes. They impact the marketing strategy, how you position product variety and upgrades, and they certainly impact product development management itself. Highly integrated designs typically require much tighter coordination and communication between different engineering disciplines because the functions are so coupled within the physical parts.
Okay, the architecture is set, at least preliminarily. Now we need to talk about how the product looks, feels, and interacts with the user. This brings us to industrial design, or ID.
Yes, ID. For engineers who are often deeply focused on the physics, the function, the tolerances, ID can sometimes, unfortunately, be seen as secondary, just making it look pretty at the end.
Just the skin.
Right. But our sources make it abundantly clear that ID, when integrated properly and early, can have a truly revolutionary impact on commercial success. It's far more than just aesthetics.
So what is the core mission of industrial design in this process?
The ID mission really focuses on all the aspects of the product related directly to the user. This broadly falls into two main areas. First, aesthetics. This includes the visual appeal, the form, the color, the finish, the product's visual equity, how it communicates brand identity.
And the second area?
The second is ergonomics and human factors. This is about the user interface. How easy is it to understand and operate? How comfortable is it to hold or use? It also covers things like ease of maintenance, overall utility, safety, and how the product feels to interact with. It's the complete user experience.
So it's transforming a functional machine into a desirable, usable product.
That's a great way to put it.
The case study cited in the material, the original Motorola RAZR phone, is just a perfect illustration of ID driving the entire product strategy, isn't it?
Absolutely iconic example. The RAZR wasn't just another phone in a crowded market back then. It became a cultural phenomenon, a defining status symbol of its era.
Why? What did ID do specifically?
The key was that the industrial designers were central to the project from the very beginning, working alongside the engineers. While engineering teams were figuring out the hinge technology and the manufacturing processes for that thin metal body, it was the ID team that defined the critical overall size, the shape, and the defining human factors.
They dictated that ultra-thin form factor.
They dictated the thinness, yes, which was revolutionary at the time. They crafted that instantly recognizable, sleek, metallic appearance. They obsessed over the tactile feedback of the unique etched keypad. It was ID that made it feel special, premium.
And that aesthetic appeal and unique feel directly translated
to intense desirability. It generated strong feelings of pride and status among owners, something very few phones had achieved before. ID fundamentally moved the RAZR from being just a communication tool to being perceived almost as a piece of jewelry, a fashion accessory. That was the power of ID in that case.
The sources also categorized products on a useful continuum, from technology-driven at one end to user-driven at the other. How does this help define ID's role?
It's a really useful way to think about how much influence ID should have. ID's role naturally and necessarily increases as the product becomes more visible to the user or involves more extensive or complex user interaction.
Give us examples on that spectrum.
Okay, so at the extreme technology-driven end, think of a component deep inside an industrial server rack, maybe a specialized processing card. Function is everything. Appearance and user interaction are minimal. ID's role there is likely very small.
Right. No one sees it.
Exactly. Now move along the spectrum. Think of a simple doorknob. It's visible, and it involves a single, albeit critical, user interaction grasping and turning. Aesthetics and ergonomics matter quite a bit here. ID needs significant involvement.
Okay.
Now go further towards the user-driven end. Consider a complex product like a laptop computer. It's highly visible, and it involves dozens of distinct user interactions. Opening the hinge, the feel of the keyboard, the responsiveness of the trackpad, the screen brightness and angle, plugging in peripherals.
Everything you touch and see.
Everything. In this case, ID needs to be deeply involved in defining almost every aspect of the user experience, working hand in glove with engineering. The usability and desirability are paramount.
So the key takeaway here seems to be that ID can't be an afterthought. It can't just be brought in at the end to style the product.
Absolutely not. For products where user experience and aesthetics are important, which is most products, ID must be involved early, concurrently with engineering and marketing. They need to be part of those initial architecture decisions, concept selections, and specification settings. This ensures that critical aesthetic requirements and usability needs are treated as core performance attributes, not just surface decoration, and aren't compromised or marginalized by technical teams focused solely on meeting purely functional, measurable specifications.
That integration seems crucial for the whole total design philosophy.
It's fundamental to it. Hashtag tag 3.3, Designing for Manufacturing and Assembly, DFMDFA.
All right, we've got our concept, the architecture is taking shape, ID is involved. Now the focus shifts heavily towards the practicalities of production, specifically cost. This brings us to DFM, or Design for Manufacturing, and its close cousin, DFA, Design for Assembly.
Yes, DFM and DFA. These are twin disciplines, really, both aimed squarely at reducing the total manufacturing cost and, often simultaneously, improving the product's quality and reliability by making the production process simpler, faster, and more robust.
And cost is just paramount, isn't it? Especially for mass-market engineered goods. It can be the single biggest determinant of commercial failure or success.
Absolutely. You can have the most innovative, beautiful design in the world, but if you can't build it at a competitive cost point, you don't have a viable product.
So in DFM-DFA, where do the costs typically lie? Where's the focus?
For most highly engineered discrete goods, things made of distinct parts like cars, appliances, electronics, the cost of purchased components is often the single largest chunk of the manufacturing cost. It can easily be 50% or even more of the total cost of goods sold.
Half the cost is just buying parts.
Often, yes. So a huge part of DFM involves optimizing the design to use standard, readily available, low-cost components wherever possible, or designing custom components in a way that minimizes their manufacturing complexity and cost.
So a core strategy in DFM is really understanding the manufacturing process constraints and the cost drivers associated with them. Designers need to know what features are easy or hard, cheap or expensive to make.
That is absolutely fundamental. This is where practical, hands-on manufacturing knowledge can save millions of dollars. It's about avoiding unnecessarily expensive features simply because the designer wasn't aware of the manufacturing implications.
Give us an example.
Okay, the sources mention one. Imagine a designer specifies a very sharp, small internal corner radius on a metal part that needs to be machined from a solid block. Aesthetically, it might look clean, but the designer might not realize that creating that very small internal radius requires specialized, very slow, and therefore very expensive machining operations, like electrical discharge machining, EDM, because standard rotating milling tools can't physically fit into that sharp corner.
Okay.
A DFM-savvy designer or input from manufacturing engineers early on would recognize this immediately. They'd suggest rounding that internal corner slightly, maybe increasing the radius just a little bit. This tiny change allows the part to be made much faster and cheaper using standard, high-speed milling tools with likely no impact on function.
So DFM is about that detailed understanding, avoiding expensive features by knowing the implications of literally every line drawn on the blueprint or clicked in the CAD model.
Precisely. It requires close collaboration between design and manufacturing engineering, starting early.
This also ties back to the production volume, doesn't it? And that fundamental trade-off between fixed costs and variable costs when choosing a manufacturing process.
Absolutely critical link. You have to choose the right process for your expected volume. It's the difference between investing heavily upfront in tooling versus paying more for each individual unit later.
Explain that trade-off.
Okay, consider processes with relatively low fixed costs but high variable costs. Traditional CNC machining is a good example. The basic machine tools are versatile, so setup is relatively inexpensive, low fixed cost, but the time it takes to machine each individual part can be long, meaning the cost per part, variable cost, is relatively high. This makes sense for low production volumes, prototypes, custom equipment, maybe early production runs.
Got it. Low volume, low fixed cost, high variable cost process.
Generally, yes. Conversely, think about processes like high-pressure die casting or complex injection molding. These require extremely expensive custom-made molds or dies of very high fixed cost. You might spend hundreds of thousands, even millions on tooling before you make a single part.
Wow, big upfront investment.
Huge. But once that tool is made, you can often produce parts incredibly quickly, sometimes in seconds, meaning the variable cost per part is extremely low, maybe pennies. This only makes economic sense if you expect to produce very large volumes, hundreds of thousands or millions of units to amortize that massive fixed cost over.
So the total design team has to accurately forecast the sales volume to make the right DFM process selection.
They absolutely must. Choosing the wrong process for your volume can destroy profitability.
Okay, that's DFM focused on making individual parts cheaper. Then we shift to DFA, design for assembly. What's the main focus there?
DFA focuses specifically on minimizing the cost of putting all those individual parts together into the final product. And the single most effective strategy for reducing assembly cost is almost always drastically reducing the overall parts count.
Fewer parts equals less assembly.
Fewer parts, less assembly time, less inventory to manage, fewer suppliers to deal with, fewer chances for assembly errors, fewer fasteners needed. The benefits cascade. Every single part you can eliminate from a design is a win.
How do you eliminate parts?
Often by designing components to perform multiple functions, or by replacing complex assemblies that involve separate screws, washers, nuts, and brackets with integrated features like snap fits, living hinges, or using a single, more complex molded or cast part that combines the functions of several simpler ones.
Makes sense. Fewer parts is generally better.
Yeah.
DFA also introduces another really essential principle, error proofing.
Yes, error proofing. It's also known by the Japanese term pokyoke. This means proactively anticipating potential failure modes during the assembly process and designing the product, or the process, to prevent those errors from happening in the first place. It's preventative quality assurance built right into the design.
Give an example of an assembly error you'd want to proof against.
Okay, imagine an assembly uses two screws that look almost identical but have very slightly different thread pitches. Maybe one is a metric M4 by 0.7 millimeter thread, and the other is an M4 by 0.75 millimeter thread. They look the same to the eye.
Right. Easy to mix up.
Very easy for an assembly worker, especially working quickly, to grab the wrong screw and try to force it in. This could damage the threads in the mating part, leading to a weak joint, a failed product, an expensive rework or strap. That's a classic assembly failure mode.
So how would DFA airproof that?
A good DFA strategy would flag this risk. Maybe the design could be changed to use the same screw in both locations, or if different screws are absolutely necessary, make them visually distinct, different head types, different colors. Or maybe design the parts so the wrong screw physically won't even start threading. The goal is to make the error impossible or immediately obvious.
What about parts that are mirror images of each other, left-hand and right-hand versions?
Yes. Asymmetric parts that look similar but must be installed in a specific orientation, left versus right, up versus down, are notorious sources of assembly errors. Good error-proofing mandates designing these parts, or their mating features, so they only fit together the correct way. Perhaps through asymmetric tabs and slots, or unique keying features, or clear visual guides molded in, make it physically impossible, or at least extremely difficult, for the assembly worker to install them backward or in the wrong location.
That resilience against simple, predictable human error seems critical for high-volume, high-quality manufacturing.
It's absolutely paramount. It saves enormous amounts of money by preventing defects before they happen.
One more nuance here. We talked about reducing parts count through integration. It seems logical that integrating functions into one single complex component is always the best DFM approach. Is that true?
Not always. It's a trade-off, like so many things in design. Integrating multiple parts into one single component is fantastic for controlling critical geometric relationships between features. Those relationships are locked in precisely when the single component is fabricated, for example, molded or machined. That can be great for accuracy and reliability, but sometimes deliberately disintegrating what could be one large complex component into two or more simpler, separate parts can actually achieve lower piece part production costs overall, even though you now have more parts to assemble.
How could making more parts be cheaper?
The source mentions an example: a complex single-piece cast metal intake manifold for an engine. Casting that intricate shape might be difficult and expensive. It was replaced by designing two simpler, separate injection-molded plastic pieces that were then joined together. Even with the added assembly step, the much lower cost of injection molding the simpler plastic parts compared to casting the complex metal part resulted in a lower overall cost.
Okay. So it's a trade-off between maybe better geometric control and reliability from integration versus potentially lower individual piece part production costs from disintegration.
Exactly. The total design team has to evaluate this trade-off carefully, using detailed cost models for different manufacturing processes, not just relying on the intuition that fewer parts is always cheaper. Sometimes, strategically adding a part boundary can unlock a much more cost-effective manufacturing process for the resulting simpler components. Hashtag TAG 3.4, Designing for Environment. DFE.
Okay, we've tackled function, cost, assembly. Moving beyond those, there's another critical design consideration, DFE, or designing for the environment.
Yes, DFE. And this represents a commitment that really goes far beyond just meeting minimum regulatory compliance standards like RoHS or energy efficiency labels.
More proactive.
It's much more proactive. It involves making deliberate decisions throughout the entire design process about material selection, energy efficiency in manufacturing and use, waste avoidance, and end-of-life considerations like disassembly and recycling, all with the goal of minimizing the product's overall environmental impact.
The source material mentions a philosophical underpinning here, drawing from ideas like the cradle-to-cradle approach. What's the core idea there?
The core idea of cradle-to-cradle and similar philosophies influencing DFE is to shift the goalposts. Instead of just trying to make products that are merely less bad or less harmful to the environment, using slightly less energy or generating slightly less waste, the aim is to move towards designing products that are truly restorative or inherently benign within ecological cycles.
So designing products whose materials can be safely returned to the soil or endlessly recycled into high-quality new products without degradation.
That's the ideal, yes. It means paying deep attention to material health, avoiding toxins, designing for easy disassembly and material separation, maximizing the use of recycled and recyclable materials, and considering the energy sources used in production.
The Herman Miller Setu chair is held up as a leading case study for successfully integrating DFE principles right from the start.
The Setu chair is a phenomenal example, yes. It really showcases materials innovation driven largely by ambitious DFE targets.
What do they do specifically?
It was designed from the ground up with environmental impact as a primary driver. They focused on material simplicity, its innovative flexible spine, which provides ergonomic support without complex mechanisms, is molded from just two types of polypropylene materials. This made it significantly lighter and far less materially complex than previous generations of ergonomic office chairs.
Less material, fewer parts. Sounds like DFM-DFA principles, too.
Absolutely. DFE often aligns very well with DFM-DFA, reducing material use, saves cost, and reduces environmental impact. The Setu was also designed for easy disassembly at end of life, using environmentally safe materials chosen for their recyclability, and Herman Miller committed to producing it using renewable energy sources.
And this intense focus on materials and production was guided by their understanding of the product's life cycle assessment, correct?
Precisely. The design team understood that for a product like an office chair, the environmental impact during the use stage, the years someone spends sitting in it, is actually relatively insignificant compared to other product types.
Unlike, say, a car or a refrigerator that uses energy constantly.
Exactly. For office furniture, the greatest environmental impacts are overwhelmingly concentrated in the materials selection, extraction and processing, the production phase, manufacturing energy and waste, and the end-of-life or recovery stage, disposal or recycling. Knowing this allowed them to focus their DFE efforts where they would have the biggest leverage on material elimination, choosing safe and recyclable materials, and clean production.
To quantify and visualize these impacts across the different stages, teams use a methodology called life cycle assessment, or LCA.
Yes, LCA is the systematic methodology for evaluating, or at least qualitatively assessing, the total environmental impacts associated with a product throughout its entire life cycle.
From cradle to grave.
From cradle to grave, or ideally, cradle to cradle. This means looking at impacts from raw material extraction, processing, manufacturing, product distribution and transportation, the use phase itself, and finally, the end-of-life management, recovery, recycling, or disposal. Tools like the LIDS wheel, Life Cycle Design Strategies wheel, are mentioned as ways to visually map and track potential improvements across these stages.
And this assessment is crucial because it tells the team where to focus their limited resources for DFE improvements. Where will they get the most environmental bang for their buck?
Absolutely. The dominant impact stage varies wildly depending on the product type. Like we said, for a gasoline, automobile, or complex electronics with high energy consumption, the use stage often dominates the lifetime environmental footprint. So focusing on fuel efficiency or reducing power consumption during use is paramount.
But for other products?
But for other products like clothing, simple tools, packaging, or indeed the Setu chair, the impacts are much more concentrated in the materials and production stages. So for these products, DFE efforts should prioritize using recycled materials, reducing material intensity, designing for durability, and minimizing manufacturing waste energy. LCA helps identify that priority.
And like ID, DFE requires early cross-functional involvement.
It absolutely has to. You can't just hand it off to an environmental specialist at the end. ID influences material choices and disassembly. Engineering decisions impact energy efficiency and material types. Purchasing needs to source sustainable materials. Manufacturing needs to implement cleaner processes. Marketing needs to understand how to communicate the environmental benefits. It requires true collaboration from the very start to ensure that a sustainable design choice doesn't inadvertently drive up costs unacceptably or compromise essential user functions or appeal. It's another core pillar of total design.
Okay, we've designed it, considered the user, optimized for manufacturing, thought about the environment, but ultimately for a commercial product, it has to make money. We need to ensure the product is actually profitable.
Absolutely. This brings us to the realm of product development economics. This provides the quantitative financial view, predicting the project's payback period, its overall profitability, and its financial viability.
And the primary tool for this evaluation is net present value, or NPV analysis.
Yes, NPV is really the industry standard for making major investment decisions in product development. It's a discounted cash flow technique.
How does it work, in simple terms?
Okay, the team has to forecast or estimate all the expected future cash flows associated with the project over its entire anticipated life. This includes the initial development investment, a negative cash flow, the costs of production ramp-up, ongoing manufacturing and marketing expenses, more negative flows, and critically, the expected income from product sales, positive cash flows.
So all the money going out and all the money coming in, year by year.
Exactly. Then, because a dollar received next year is worth less than a dollar in hand today, due to the time value of money and risk, you discount all those future cash flows back to their equivalent value in today's terms. You use the company's required rate of return or hurdle rate as the discount factor. Finally, you sum up all those present values, the discounted negative flows, costs, and the discounted positive flows, income. If the final sum, the net present value, is positive, then the project is deemed theoretically financially worthwhile. It's expected to generate more value than its cost, considering the time value of money and risk.
That seems straightforward enough conceptually. But for the project team actually managing the investment day to day, what's the most critical financial concept they need to internalize from this?
Without a doubt, it's the importance of ignoring sunk costs.
Sunk costs, explain that. Why is it so critical?
Some costs are money that has already been spent and cannot be recovered. It's water under the bridge. This could be investment in previous failed design iterations, prototypes that were canceled, market research conducted last year, any past expenditure.
Okay, money already gone.
Right. And the fundamental principle in finance, though, it often clashes violently with human psychology and organizational politics, is that sunk costs are completely irrelevant to future investment decisions. They must be ignored when you're calculating the NPV of a future course of action, like deciding whether to continue funding a project today.
But that must be incredibly hard in reality. People get attached to projects they've poured money into. Organizations want to justify past spending.
Extremely hard. People are emotionally invested, careers can be on the line, managers hate to admit a past decision was wrong. The classic example the sources might use is the team arguing over a prior $600 million investment in a project that's clearly struggling.
Okay.
Now they face a decision. Should we invest an additional $90 million today to try a new approach to salvage it? The sunk cost fallacy is to say, we've already spent $600 million, we can't just walk away now.
Right, we have to keep going to justify the initial investment.
Exactly. But financially, that $600 million is gone. It's sunk. It's irrelevant to today's decision. The only question that matters is, based on our best current estimates, will the expected future profit generated solely by this new $90 million investment outweigh that $90 million investment? If yes, maybe proceed. If no, you cut your losses, regardless of the $600 million already spent.
So ignoring sunk costs prevents throwing good money after bad, simply to justify past mistakes.
Precisely. It's about making rational decisions based on future prospects, not past expenditures. It requires real discipline.
Okay, so you build this base case financial model using NPV, ignoring sunk costs. But forecasts are always uncertain. What's the next step to understand the project's robustness?
The next crucial step is to perform sensitivity analysis.
Sensitivity analysis, what does that involve?
Sensitivity analysis takes your base case financial model, the NPV calculation with your best guess inputs, and systematically modifies the key assumptions one at a time to answer what-if questions. What happens to the project's NPV if sales volume is 20% lower than expected? What if production costs are 10% higher? What if the development takes 6 months longer?
So you see how sensitive the project's profitability is to changes in the key variables.
Exactly. And the analysis helps you differentiate between two broad types of factors driving that sensitivity. First, there are internal factors, things the development team has relatively high influence or control over.
Right.
Things like total development expense, the final production cost per unit, and the overall development speed or time to market.
Okay, internal factors. And the second type?
The second type are external factors, things largely outside the team's direct control, driven more by the market or competitors. Things like the actual sales volume achieved, the competitive pricing environment, can we maintain our target price, required marketing and sales expenses, maybe even shifts in component costs due to external market forces.
And this sensitivity analysis points you towards the biggest risks.
Precisely. It identifies which assumptions, if they turn out wrong, will have the biggest negative impact on the project's financial success. For instance, the AB100 case study mentioned showed that the project's NPV was extremely sensitive to the initial sales volume achieved. A 50% drop in volume below the forecast caused a massive 64% negative swing in the project's calculated NPV. Much more sensitive than, say, development cost overruns.
So knowing that tells the team where to focus their risk mitigation efforts.
Yes. If your project is highly sensitive to sales volume, maybe you need to invest more heavily in early market testing, or secure pre-launch orders from key customers, or develop contingency marketing plans. If it's highly sensitive to production cost, then DFM efforts become even more critical. Sensitivity analysis guides proactive risk management.
And linking this back to how projects are managed, Having structured decision points or milestones throughout the development process actually enhances the financial value, doesn't it?
It does. This relates to the concept of real options in finance. The calculated NPV of a project isn't necessarily fixed from day one. Its true financial value is actually enhanced by the flexibility the organization retains to modify, delay, expand, or even abandon the project at key decision points, milestones, as new information becomes available.
So you don't have to commit all the funding up front.
Ideally, no, especially for high-risk projects. Where technical or market uncertainties are unusually large, the first phase of development might be deliberately designed to be relatively small and inexpensive. Its main goal might simply be to resolve a major technical risk or validate a key market assumption before the much larger commitment to full-scale development and tooling investment is made. This staged investment strategy, preserving the option to pull the plug if early results are bad, increases the project's real option value and reduces downside financial risk. #HighTech 4.2, managing the project timeline and complexity.
Okay, we understand the economics and risks. Now let's shift to the practicalities of execution, managing the project timeline and the sheer complexity of coordinating all these activities.
Right, project management is critical, and visualizing the plan is the first step. Teams commonly use tools like Gantt charts, which show tasks laid out against a timeline, and also arrow network diagrams, like PERT charts, which are better at explicitly showing the dependencies between tasks.
And flowing from those dependency diagrams is the central, absolutely crucial concept for managing the schedule. The critical path method, or CPM.
CPM is fundamental. You cannot effectively manage a complex project schedule without understanding the critical path.
So define the critical path for us again. What is it?
The critical path is the specific sequence of interconnected tasks, from the start of the project to the end, that determines the shortest possible duration for completing the entire project. There might be many parallel paths of activity happening, but the critical path is the longest one in terms of time.
Meaning, if any task on that specific path gets delayed.
If any task on the critical path is delayed by even a single day, the final completion date of the entire project slips by a day. There's no buffer.
But other tasks, not on the critical path, might have some wiggle room.
Exactly. All the other paths through the project network, the non-critical paths, contain some degree of slack or float. Slack is the amount of time a task or a sequence of tasks on a non-critical path can be delayed without affecting the overall project completion date.
Why is identifying this critical path so essential for project managers?
Because it tells them precisely where to focus their management attention and limited resources. If you need to accelerate the project, you must shorten tasks on the critical path. If resources are constrained, you prioritize keeping critical path tasks on schedule. If a non-critical task faces a minor delay, you know you have some slack to absorb it without panicking about the launch date. It allows for targeted control.
Okay, CPM helps manage the overall timeline. But for really complex, cross-functional projects, just seeing the sequence isn't enough. You need to visualize how the different tasks and teams truly interact and depend on each other. For this, the sources highlight the Design Structure Matrix, or DSM.
The DSM is an incredibly powerful visualization tool, especially for complex engineering projects where information flow is messy.
How does it work? What does it look like?
Imagine a square grid, a matrix. You list all the major development tasks or teams down the rows, and you list the exact same tasks or teams across the columns, usually in the expected chronological order of execution.
Okay, tasks listed both ways. Then what?
Then you go through the matrix and place a mark, like an X, in a cell to indicate an input-output relationship or a dependency. Specifically, if the task listed in a given row needs information from the task listed in the corresponding column in order to proceed, you mark that cell.
So it maps out who needs what from whom. What makes the DSM particularly insightful? The sources emphasize the placement of marks relative to the main diagonal of the matrix.
Absolutely, that's the key insight. Marks that appear below the diagonal represent dependencies where information flows in the expected chronological direction. Task B needs input from Task A, and Task A happens earlier. That's normal sequential flow.
Okay, but what if a mark appears above the diagonal?
A mark appearing above the diagonal is highly significant and immediately flags a problem area. It reveals that two or more tasks are coupled or interdependent.
Coupled, meaning?
It means there's a circular dependency. Task A needs information from Task B to finish, but because Task B is scheduled to happen later than Task A, Task B also needs information, maybe preliminary designs or feedback, from Task A to even get started properly. They depend on each other.
Feedback loop or iteration is required.
Exactly. An X above the diagonal visually screams, These tasks cannot be done sequentially. They require intensive, rapid, probably iterative information exchange between the teams involved. The DSM instantly highlights not just the technical dependencies, but also the inherent organizational, communication, and coordination challenges the project team will face. It shows you where the real management headaches are likely to be.
That's really useful for structuring communication. Now, the ultimate goal is often to accelerate the project, to get to market faster. How do teams effectively compress the schedule, especially knowing these dependencies?
There are two main approaches discussed for accelerating projects. The first involves directly tackling those dependencies to shorten the critical path. It's about overlapping sequential tasks more aggressively.
Which is the core idea behind concurrent engineering.
Precisely. Concurrent engineering, or simultaneous engineering, challenges the traditional waterfall model, where one phase must be 100% complete before the next begins. If the testing task normally waits until the design task is fully finished and documented, concurrent engineering says, why wait? Let's start testing the initial design modules when the overall design is maybe only 80% complete.
But doesn't that increase risk if the design changes later?
It does increase risk and requires much better communication and coordination. You need rapid and reliable information exchange between the design and testing teams and others to manage the interdependencies highlighted by the BSM. You might have to redo some tests if the design changes significantly. But the potential time savings from overlapping these long sequential tasks can be enormous, dramatically shortening the critical path.
Okay, overlapping tasks is one way. What's the second major approach to keeping projects on schedule or even accelerating them?
The second approach requires immense discipline, especially from the project team and management. It's aggressively managing the project scope.
Scope management, meaning preventing things from getting added.
Exactly. It means actively fighting against feature creep, or what's sometimes called creeping elegance. This is the very natural, almost universal human tendency for engineers, designers, and marketers to want to add just one more cool feature or make its part a little bit better as the development process progresses and they learn more.
Those small additions seem harmless, but they add up.
They add up massively. Each small addition requires design changes, testing, documentation updates, potential manufacturing process adjustments. It ripples through the entire project, inevitably causing delays and budget overruns. Disciplined, successful teams understand that they must be able to freeze the design at a predetermined point.
Draw a line in the sand.
Draw a line, launch the product with the agreed-upon feature set, and consciously save those incremental improvements or new features for the next generation product, version 2.0. Trying to constantly tweak and enhance the current project is a recipe for never finishing on time or on budget. Effective scope control is paramount. Hashtag 4.3, engineering for reliability and robustness.
So project execution isn't just about hitting the schedule and budget, it's fundamentally about making sure the final product actually works reliably in the real world. It needs to withstand the variations it will inevitably encounter.
Absolutely. This brings us to the crucial concepts of reliability and robustness in design. Specifically, the sources highlight robust design methodologies, heavily influenced by the work of Junichi Taguchi.
Robust design, what's the core goal there?
The core goal of robust design is to make the product's performance insensitive to variations that the design team cannot fully control during either manufacturing or the product's use. These uncontrolled variations are often called noise factors.
Noise factors, like what kind of variations are we talking about?
Noise factors can come from many sources. There's external noise, variations in the operating environment, like ambient temperature changes, humidity, dust, vibration. There's unit-to-unit noise, slight differences between products due to unavoidable manufacturing tolerances stacking up. There's deterioration noise, the product's performance changing over time due to wear, aging, or material degradation. And there's user noise, different users operating the product differently, perhaps even making errors.
Okay, lots of sources of variation. So how does the team actually apply robust design principles to combat this noise?
They typically conduct structured experiments, often using statistical methods like design of experiments, DOE. In setting up these experiments, they carefully define three key types of factors.
What are the three types?
First, you have the performance metrics, the critical outputs you want to control and make robust. Example, the brightness consistency of an LED, the closing force of a car door, the battery life of a device.
Okay, what you're measuring.
Second, you identify the likely noise factors, those uncontrolled variations you expect the product to encounter, e.g. range of operating temperatures, expected manufacturing tolerance ranges, different user strengths.
The things you can't control but need to withstand. And
Third, and most importantly, you define the control factors. These are the design parameters that the engineering team can specify and control things like material choice, component dimensions, circuit parameters, software algorithms, assembly procedures.
got it. Control factors are the knobs the designers can turn.
Mm.
So the objective of the robust design experiment isn't just to hit the target performance value on average.
No, that's the critical distinction. The objective is not just to get the average performance on target. It's to find the specific settings for the control factors that make the performance metric least sensitive to the variations induced by the noise factors. You want to minimize the variability around the target performance, even when the noise factors are fluctuating wildly within their expected ranges.
Can you give an example?
Sure. Think about a cell phone camera. A robust camera design would take consistently good pictures, good brightness, color balance, focus, whether you're shooting in bright sunlight, high noise, or dim indoor artificial light, different noise. The control factors, lens design, sensor specs, image processing algorithms, have been chosen specifically to minimize the effect of the noise factor, ambient lighting condition, on the performance metric, image quality.
So quality, in this Taguchi-influenced view, is really about consistency and minimizing variation in the face of noise.
Exactly. Taguchi famously defined quality as the minimization of the total loss imparted to society by the product after it is shipped. That loss includes not just warranty costs, but also customer dissatisfaction due to inconsistent performance caused by sensitivity to noise factors. Robustness equals high quality.
That's a powerful way to think about it. Now, a complementary tool focused more on preventing outright failures rather than just performance variation is FMEA.
Yes, failure mode and effects analysis, or FMEA. It's another systematic technique, but it takes a different approach. While robust design focuses on minimizing sensitivity to variation, FMEA focuses on identifying potential ways the product could actually fail completely.
How does FMEA work?
It's typically a bottom-up process. You start by looking at individual components or subsystems. For each one, you brainstorm. What are all the possible ways this component could fail? These are the failure modes. Then, for each failure mode, you analyze. What would be the consequence, the effect of this failure on the overall system performance or safety?
So if this seal leaks, what happens? If this sensor gives a wrong reading, what's the result?
Precisely. Then you typically assess the severity of that effect, the likelihood of that failure mode occurring, and how easily that failure mode can be detected before it causes harm. Based on these assessments, often resulting in a risk priority number or RPN, the team can then prioritize preventative actions, maybe redesigning the component, adding redundancy, implementing stricter quality control checks, or adding warning systems.
So FMEA is really about systematically anticipating and mitigating potential catastrophic failures.
Yes, it's crucial for quantifying and reducing risk, especially in critical areas of the design like structural components, safety mechanisms, or core functional systems. It ensures you've thought through the what-ifs.
Finally, let's talk about prototypes. They're obviously used throughout the testing and refinement phase, but the sources emphasize they serve multiple distinct goals, not just finding bugs.
That's right. Prototypes are essential tools, but you build different types for different reasons at different stages. They serve technical learning, risk reduction, communication, integration testing, and meeting milestones.
What about early prototypes?
Very early in the process, you might build simple proof of concept prototypes. These aren't full products. They're often just focused on answering a specific technical question or validating a risky new technology or mechanism. Can we even make this core function work? The goal is purely technical learning.
Okay. Then as you move closer to launch, the distinction between alpha and beta prototypes becomes really important for managing risk.
Yes, the alpha-beta distinction is critical.
So what defines an alpha prototype? When and why do you build those?
Alpha prototypes are typically built relatively early in the testing and refinement phase. The key characteristic is that they are built using the intended production materials and the final product geometry. The design is essentially frozen at this point, at least in terms of form and materials.
But they might not be made using the final factory processes.
Correct. Alpha prototypes are often fabricated using slower, more flexible prototype methods like CNC machining or simpler tooling, not necessarily the high-volume production tooling and assembly lines. Their primary purpose is internal testing.
Tested by the engineering team.
Usually, yes, or maybe by specialized internal test groups. The goal is to verify, does the product work as designed? Does it meet the key performance specifications we set? Does it satisfy the core customer needs in a controlled environment? It's about internal functional verification and finding major design flaws before you commit to expensive production tooling.
Okay, that's alpha. Then what are beta prototypes?
Beta prototypes come later in the process, after alpha testing has confirmed the basic design works. Beta prototypes are typically built using parts that were supplied by the intended final production processes and using the actual production tooling, or close approximations.
So they represent what will actually come off the assembly line.
Much more closely, yes. Though they might still be assembled offline, not necessarily on the final high-speed line yet. The crucial difference is where they are tested. Beta prototypes are extensively evaluated externally by actual customers in their own real-world use
To
environments.
see how it holds up in the wild.
Exactly. The goal of beta testing is focused on reliability, durability, finding more subtle bugs or usability issues that only show up under real-world conditions. Remember those noise factors. Getting final customer feedback and identifying any last-minute critical engineering changes needed before full production ramp-up.
And you also mentioned communication as a function of prototypes earlier. How do they help with that?
A physical prototype, even a non-functional one, can often communicate design, intent, constraints, or complex spatial relationships far more effectively than drawings or CAD models alone.
Having something tangible to hold and see.
Yes. The example given is the iRobot PackBot, the military robot. They used early look-and-feel prototypes, physical mock-ups, likely made using rapid prototyping like 3D printing, specifically to communicate the precise physical size of the robot, and, importantly, the very limited crush zone or space available for adding new payloads or sensors.
So it helped managers and customers understand the physical limitations.
Instantly. Trying to explain those tight spatial constraints verbally, or even with complex CAD cross-sections, might be difficult. But putting a physical model on the table makes the limitations immediately clear and tangible for everyone involved: managers making decisions, customers providing feedback, engineers designing add-ons. Prototypes are powerful communication tools. Hashtag outro. So if we try to synthesize this whole systematic process, this idea of total design, I think the key insight is that successful product development is fundamentally a rigorous management and evaluation challenge that guides and harnesses that initial spark of invention. It's not just about having clever ideas.
Right. The execution and the process around the idea are just as important, if not more so.
Absolutely. The most successful teams, the ones that consistently bring winning products to market, they move beyond guesswork or relying solely on intuition. They employ systematic methodologies throughout the process, whether we're talking about pew charts for concept screening, detailed DFM checklists and rules of thumb, or rigorous NPV and sensitivity analysis for financial evaluation.
They're constantly navigating those trade-offs we discussed.
Constantly, systematically navigating the intrinsic trade-offs required to optimize performance, minimize cost, ensure manufacturability, meet user needs, and mitigate both technical and financial risk. It's a complex balancing act managed through process.
And crucially, all of this detailed methodology, all these steps, they rely heavily on the underlying organizational structure, whether it's functional, project, or that complex matrix being set up to actually support the small, focused core team in executing the plan.
That's a critical point. The structure has to enable, not hinder. It must facilitate that rapid, intensive information exchange, especially for those couple tasks we saw in the DSM that's needed to resolve conflicts, make decisions, and finalize all the details.
Culminating in, what's the final output of all this effort?
Well, remember, the ultimate output of this entire systematic product development process isn't just a shiny new physical product sitting on a shelf. It's also the complete package of control documentation.
Control documentation.
Yes, the finalized, validated, released engineering drawings, the detailed 3D CAD files, the precise material specifications, the quality control plans, the manufacturing process instructions, the assembly sequences, everything necessary for the factory floor, potentially thousands of miles away, to reliably and repeatedly produce millions of identical, high-quality, profitable units. That documentation package is the culmination of total design.
Okay, so there's one final takeaway for you, the listener, the learner from this deep dive. What should it be?
For me, it comes back to the beginning. Whether you're developing a massive piece of industrial equipment or tackling a complex internal software project, arguably the most valuable early step you can take is that systematic, rigorous translation of fuzzy goals like high-level customer needs or business objectives into precise, measurable, technically feasible targets, your specifications.
Nailing down those specs before you commit to a solution.
Yes. If you skip that step or rush through it, if you leave the targets vague, the entire subsequent design and development process is left vulnerable to guesswork, misinterpretation, endless feature creep, and ultimately significant financial and market risk. Get the targets right first.
That's a great takeaway. Get the targets right.
And that leads me to maybe a provocative final thought for you to consider, building on all this. We rely heavily today, as we've discussed, on established design heuristics, those rules of thumb that engineers have developed through decades of experience in areas like DFM, DFA,
That's
DFA.
collected wisdom.
Exactly. But if you consider the level of seamless, simultaneous integration of knowledge that optimal total design seems to require now, combining cost implications, environmental impacts, complex user needs analysis, supply chain constraints, maybe even predicting competitor moves, all feeding into a single design decision model, what might the next truly revolutionary design methodology look like?
You mean beyond our current tools?
Yes. Specifically, what methodology might be created not by human experience alone, but by sophisticated artificial intelligence? Could AI develop systems that seamlessly optimize across DFM, DFE cost, performance, and customer satisfaction in real time in ways humans currently can't? And if so, how must human designers adapt their roles and skills when those complex systematic evaluation and optimization processes become increasingly automated and integrated across the entire total design playbook?
Wow. That's definitely something to think about, how AI might reshape this entire systematic process we've just explored. Fascinating place to leave it. Thank you for that deep dive.
My pleasure.